We'll start now. So are you telling us this topic? Is the topic correct or not?
This is my FYP topic.
Okay, but what's the real thing you're talking later? Like what's in
Yeah, I
your
have an
content?
introduction saying what I'm talking in this project.
Okay, sure.
Okay.
Yeah, start.
Can I start? Okay.
Yeah, you may start.
Good afternoon, professors. My name is Pangdingyu, and my student ID is MAT2209460. The topic of my final year project is Hugaya Seta category of mutant fiber of type B boundary singularity. And today I will discuss some fundamental knowledge which will help to research deeper in this topic. Okay. Sorry. Okay. So in this project, we will introduce the flows and the Hamiltonian vector fields and their relations. Before starting, we need to know about symplectic manifolds, which will be used in this project. A symplectic manifold is a pair M omega, where M is a manifold, and omega is a symplectic form on M. A symplectic form, by definition, it is closed and it is a differential two-form. First, let's define the integral curves. Let X be a vector field on a smooth manifold M, and integral curve of X is a differentiable curve gamma defined on a open interval such that gamma prime t is equal to x gamma t for all t in J. And in addition, if 0 in J, we will call gamma 0 the starting point of gamma. We can also say gamma starts at gamma 0. Then let's introduce the rescaling lemma and translation lemma. Let X be a smooth vector field on a smooth manifold M. Let J be an open interval, and gamma be an integral curve of X. Then, for any constant A and B, the curve gamma bar T, defined by gamma bar T is equal to gamma A T plus B, is an integral curve of AX. Notice that the domain of this new curve is defined by all t such that at plus b is in J. This is for the well-definedness of gamma bar t, because it has a formula of gamma at plus b. Yeah. Now we can prove this proposition. To show gamma is an integral curve of AX, by definition, we need to show that gamma bar prime t is equal to AX evaluated at gamma bar t. So by definition, we have gamma bar t is equal to gamma at plus b, and by chain rule, we can differentiate it both sides, and we can get gamma bar prime t is equal to A times gamma prime at plus b. Since we know gamma is an integral curve of X, by the definition of integral curves, we have gamma prime at plus b is X evaluated at gamma at plus b, which is by definition just gamma bar t. Hence, we have gamma bar prime t is equal to A times gamma x gamma bar t, and by the definition of scalar multiplication of vector fields, we can put AX together. So gamma bar prime t is equal to AX evaluated at gamma bar t, and it proves that gamma bar is an integral curve of AX. So now let's go to the flows. Before that, we need to know what are flow domains. So let's M be a smooth manifold. A flow domain for M is an open subset D of R times M, such that for each point P in M, the set dP defined by all T in R such that TP is in D is an open interval containing 0. So we can define flows now. Let M be a smooth manifold. A flow on M is a continuous map phi from D times M to M, where D is a flow domain satisfying, firstly, for all P in M, we have phi 0P is equal to P. And we have phi T, phi SP equal to phi T plus SP for all S in DP and T in D phi SP, such that T plus S is in DP. Based on flows, we have some useful definition. So if we fix the t, we can have a function phi t defined by phi tp equal to phi tp. It is a homeomorphism on M because it is easy to see that it is easy to check that phi minus t is its inverse. So, and if in addition phi is smooth, then it is a diffeomorphism. On the other hand, if we fix the points P on M, we can have a curve defined by phi pt equal to phi tp. It is a curve on M defined on dp. So then the infinitesimal generator is defined to be a function from M to its tangent bundle defined by it maps every P in M to tangent vector phi p prime 0. Also, a maximal integral curve is an integral curve whose domain cannot be extended, and maximal flow is a flow whose domain cannot be extended. So now let's go to the fundamental theorem on flows. Let X be a smooth vector field on a smooth manifold N. There is a unique smooth maximal flow whose infinitesimal generator is X, and which satisfies for each P in M. The curve phi p is the unique maximal integral curve of X starting at P. Since the fundamental theorem on flows determines a unique maximal flow for generated by a smooth vector field, we will call the flow phi the flow of X. The proof of the fundamental theorem on flows is involves a lot of analysis and it is kind of tedious, so we will only do a sketch of proof here. So firstly, for each P in M, it can be shown that there exists an integral curve of X starting at P. This is the existence of integral curves. Moreover, if we fix an interval J, the integral curve defined on J should be unique. So this existence and uniqueness statement are fundamental properties of integral curves, and we shall omit it here, omit the proof here. Then let's dp be the union of all open intervals J in R containing 0, on which the integral curve starting at P is defined. By construction, we know D is a flow domain. And by the uniqueness statement we introduced above, there is a unique maximal integral curve defined on dp. And we can let our phi p to be this curve. Therefore, phi would be a maximal flow. And it is also easy to check phi X is indeed the infinitesimal generator of phi. So to check X is the infinitesimal generator of phi, by definition, we need to check that xp is equal to phi p prime 0. So we start from phi p prime 0. Since phi p is an integral curve, by the definition of integral curve, it is equal to x phi p 0. And by definition of flow, we also know that phi p0 is just p. So we have xp is equal to phi p prime 0, which implies that X is the infinitesimal generator of phi. Then we will define the Hamiltonian vector fields. Let M be a symplectic manifold with symplectic form omega, and let H from M to R be a smooth function. We define the Hamiltonian vector field XH from M to its tangent bundle by the equation omega p dot xhp is equal to dhp for each p in M. Or equivalently, we can define the Hamiltonian vector field by integral product. It is defined by iota xh omega is equal to minus dh. This definition is simple, but there is a point we need to be take some attention. So recall the Hamiltonian vector space XH, its definition is here. So we need to check the well-definedness of XH. For each point P in M, we define the linear map aside from the tangent space TPM to the cotangent space TP star M. And psi maps each P to a cotangent vector omega P dot V. And by the non-degeneracy of omega P, we know that psi must has kernel 0, which means that it has a trivial kernel. So by the knowledge of linear algebra, we know that psi is an isomorphism. So it is bijective and psi inverse is well defined. So it is easy to see that XH is actually the composition of psi inverse and DH. Therefore, XH is also well defined. Moreover, since we know that both components of this composition is smooth, so XH is also smooth. We'll talk a little about Lie derivative here. So let X be a smooth vector field on a smooth manifold N, and let phi be the flow of X. The Lie derivative with respect to X is defined by Lx, which maps K form alpha to d over dt phi t star alpha evaluated at t equal to 0. Here, phi t star means that the pullback of phi t. Below is a theorem known as Cartan's formula. It relates the Lie derivative, extra derivative, and inter products. And it states that Lx is equal to d iota x plus iota dx, iota xd. Before go to the last theorem, we need to prove a lemma first. Let X be a smooth vector field on a smooth manifold M, and let phi be the flow of X, and we take a differential form alpha on M. Then the Lie derivative of alpha is equal to 0 if and only if the pullback of phi t maps alpha to alpha itself. So let's prove this lemma. And the converse proposition is simpler, so we'll prove it first. For if we assume phi t star alpha is equal to alpha for all t, then let's evaluate the Lie derivative of alpha. It is defined by d over dt phi t star alpha evaluated at t equal to 0. But by assumption, we know that phi t star alpha is just alpha. So we can replace it by alpha. And we know alpha is independent from t. So d over dt alpha is just 0. Then another direction, if we assume the Lie derivative of alpha is equal to 0, instead of directly evaluate this formula, we add a d over dt evaluates at t equal to t0 before that. And by the definition of first derivative, we can read it as a limit form like this. And for this phi t naught plus s star, we can read this sentence. We note it here because it involves some techniques. So for phi t naught plus s, by definition of flows, we can split it into phi t naught compose phi s. And by the property of pullback, we can separate it into the multiplication of two pullbacks. So we go back to this. To this proof. So we will have a phi t naught star here and also a phi t naught star here. So because it does not depend on s, we can put it out here. And the left part of the limit is exactly, we can notice that it's exactly the Lie derivative of alpha. But by assumption, we know the Lie derivative of alpha is just 0. So this formula is just equal to 0. So what does it mean by this equal to 0? d over dt evaluates the rate of change of phi t star alpha along t. So if it's equal to 0, then this one must be a constant. So we can write phi t star alpha is equal to phi 0 star alpha. And we know phi 0 is the identity and its pullback is also the identity. So it's also a alpha. So finally, this is the last theorem today. So let phi be the flow of a Hamiltonian vector field XH on a symplectic manifold N. For each t, the function phi t is a diffeomorphism that preserves the symplectic form omega. So for the first statement, phi t is a diffeomorphism. This is a direct solution by the fundamental theorem on flows. So we only need to show that phi t preserves the symplectic form omega. And by the previous lemma, we know that it is equivalent to show that the Lie derivative of omega is equal to 0. So by Cartan's formula, we first read the Lie derivative into d iota xh omega plus iota xh d omega. So for the first one, notice that we have iota xh omega, and we can check the definition. We can back to check the definition. We have this definition here. Iota xh omega is just equal to minus dh. So we can replace it with minus dh. And for the second one, we have d omega here. Since we know omega is a symplectic form, so it is closed. So d omega is just 0. And also we know that the external derivative is nilpotent. So by its nilpotency, we know that double d is also 0. Therefore, we proved that the Lie derivative of omega is equal to 0, and by the previous lemma, it shows that phi t preserves omega. This is all of my today's presentation. Thank you for listening.
Okay, good.
Any
Okay.
question from Qinghao?
Okay, good. So I don't really have questions. I understand this, but like I can say something like for example, like if in the Euclidean case, the fundamental theorem of integral curve is basically the existence and uniqueness of solution of a ODE. That's basically that. And metaphor locally is just Euclidean, so that's the essential of that theorem. And also that's interior product, not interior product. Yeah.
Interior product, I think.
Yeah, interior product.
Okay.
Yeah.
I don't know the pronunciation.
Yes, and
Interior product. Okay.
Interior product. Yeah, and the reason you can identify the vector and one form is because the symplectic form is non-degenerate. Like that's the critical point.
Yes.
Okay. Okay, I think that's what I want to say. Okay, it's okay. It's clear enough.
Okay. Interior product sometimes they call contraction, right? Contraction.
Yes, contraction. And D is exterior, right? You have the DI plus ID.
Mm-hmm.
It's like exterior derivative and interior product.
Mm.
Yeah.
D is an exterior derivative, and then iota is a interior product. Yeah, okay.
Yes. So they work together and then become.
Okay. In that case, thank you.
Okay,
thank you.
We can conclude this talk.
Qinghao, are you saying something?
No problem. We can conclude this talk.
Okay, thank you. So who